I welcome you all in this lecture on performance measures for second order systems, which is a sub module for modeling and simulation of dynamic systems course, which you are going through. We have seen in previous lectures the modeling of the second order systems, okay. And now in this lecture what we will see is that how the system behaves, how can we measure the performance of the system, okay. And these performance can be measured in terms of certain quantitative parameters. So, we will be seeing all those quantitative parameters, and then I will take an example to illustrate how we can evaluate these quantitative parameters. So, there are some parameters by which we can specify the performance of an underdamped second order system to a step input, okay. And these parameters are say delay time, rise time, peak time, maximum overshoot and the settling time, okay. And these parameters, yes, these by going through these parameters we can say about the behavior of the system. And not only that, if we know all these parameters for a system, even we can create the system behavior, okay, with the help of these parameters. So, let us take the first one, the delay time, which is represented here by T D, okay. The D subscript basically tells for the delay, and of course T indicates the time, the delay time. Now, you can see that here in this plot I have plotted the output x with respect to the omega t, okay, where omega is the angular frequency, fine. And this is the typical behavior of a second order undamped system, second order system, underdamped system, and when it is subjected to a step input, okay, as we have seen. So, second order underdamped system subjected to a step input. So, in this behavior we can see that there are various parameters, as I talked to you, has been defined. The delay time T D is basically this, that is this parameter, that is the T D, and it is the time required for the response to reach half of the final value at very first time, okay. So, half of the final value means basically we are talking about the steady state value, okay. So, if the steady state value of the system is xs, so the delay time is basically the time required for the system to go or reach up to the 0.5 times of the steady state value very first time, okay. So, this is how we define the delay time. Next time is the rise time, okay, and you can see in this figure that this is the rise time represented by T R, and this is basically the time required for the system to reach up to the steady state value, okay. So, as you can see, it is the time taken for the response to rise from 0 to the steady state value xs, okay. And it is actually it actually indicates, or it is a measure of how fast your system responds to the input signal, okay. So, with the rise time we can judge about the system behavior, that is how quickly the system responds to the given input, okay. It is the time for a oscillatory response to complete a quarter of a cycle basically, or that is the pi by 2 value. Okay. So, from here we can see that this omega TR is equal to pi by 2, and this is how the rise time is defined. Okay. For overtime system, TR is considered as the value for rise of response from some percentage of steady state value. Okay. That is, we can say that, say from 10% to 90%, whatever time is required, okay, for the output response to reach, and that is defined as the rise time for the overtime system. But as I said, for the undertime system, we define it as the time taken for the system to for the output to go from 0 to the steady state value. Next is the peak time. Now, if you look at this plot, you can see that this is the maximum value of the response x which the system could reach. Okay. So, actually the peak time corresponds to the time, okay, by which the system attains the peak value. Okay. And as I said, it is the time taken for the response to rise from 0 to the first peak value, and this is how it is defined, and it is the time of the oscillating response to complete one half of the cycle. So, we write here omega Tp is equal to pi, and from here we can find out the Tp value, okay, that is pi by omega. Then next parameter is maximum overshoot MP, okay, which is represented in short form by MP. So, here you can see that the value above the steady state value, this is what is we call it as the overshoot, or this is also called as the maximum overshoot here in this case. Okay. So, it is the maximum amount by which the response exceeds the steady state value. Okay. And it is the amplitude of the first peak basically. Okay. And that is what is called as the maximum overshoot. Now, overshoot is written as percentage of the steady state value, and the maximum percentage overshoot directly indicates the relative stability of the system. Okay. How your system is stable or not, or that indication is given by the maximum percentage overshoot. Okay. So, we can find out how can we determine this overshoot or the maximum percentage overshoot. Okay. So, for underdamped oscillations of the system, we have seen in our last class, that is last lecture, that we can give the for underdamped oscillation of the system, the amplitude x output is given by this relationship, okay, plus the steady state value. So, basically this portion corresponds to the transient behavior, plus this is the steady state behavior, okay, or value corresponding to the steady state. Now, as we have been noting, x steady state, if I represent it by xs, it is this equation basically. Okay. But you see that at t is equal to 0, x is equal to 0, this is the response as we have seen. So, if I substitute this here, this 0, and here this value will become 1, and this value will become 0, this value will become 1. So, what I will get essentially is that p is equal to minus of xs. Okay. And first overshoot occurs at omega t is equal to pi. This is how we have defined the peak time also. Okay. So, here I can just write expression for t as pi by omega, and if I substitute this value of t in this expression, this is what I get, minus eta omega n pi by omega, and here this p is minus xs, and this value will become minus 1, and of course this value will become 0 plus xs. That is what is going to be there, and here I am writing this omega d basically is omega. Okay. So, if I do that, these minus minus will get multiplied. So, you will have x here. So, x is equal to xs e to the power minus eta zeta omega n pi by omega plus xs. Okay. So, this is what expression we had. I can take this xs in the left hand side, and this is x minus xs is basically the overshoot value. Okay. And so, this overshoot value is given by this expression. So, this overshoot will be xs into exponential of this particular part. Okay. But you see, I have been telling you that this omega is nothing but our omega d value, that is the damped natural frequency. So, what I can do that we have derived it omega d in the last lecture as omega n under root 1 minus zeta square. Okay. So, here I can substitute for this, this is basically your damping ratio. So, I can substitute for this value here. So, I get the maximum overshoot as xs into e to the power this particular parameter, where I have substituted for here omega d, and so this omega n and this omega n will be getting cancelled, and this is what I get. So, this is maximum overshoot. Okay. And I can find out the maximum percentage overshoot just by dividing this by xs here. This is what I get, the maximum percentage overshoot, and this is in terms of the damping ratio. Okay. So, as you can see that as the damping ratio changes, your percentage peak overshoot changes. Okay. So, here I can substitute the different values of damping ratio, and I can find out what is my percentage overshoot. So, say a damping ratio of 0.2, the percentage overshoot turns out to be 52.7, for 0.4 it is 25.4, for 0.6 it is 9.5, and for 0.8 it is 1.5. So, you can see that as the damping ratio increases, the percentage overshoot decreases. Okay. And so, this is how the system behaves with the change in the value of damping ratio. Okay. Then we can define the subsidence ratio or the decrement. Okay. This actually provides the information about how fast the oscillations decays. Okay. How fast the oscillations decays and the system reaches to the steady state. Okay. So, if you want to find out that value, we can find out this decrement, and this is defined as ratio of second overshoot to the first overshoot. Okay. So, the first overshoot occurs at omega t is equal to pi, and the second overshoot occurs as omega t is equal to 2 pi. So, the first overshoot here I can write here, this is in fact the expression which we have derived earlier. Okay. And for the second overshoot I can replace this pi value with the 2 pi here. Okay. So, this is the second overshoot I can find out by replacing pi by 2 pi here, and then I can find out the decrement, that is the ratio of second overshoot by first overshoot. So, this is the ratio which I get. So, this way we can define the decrement, and as I said, it essentially tells you that how quickly your system is reaching to a steady state condition. Next important factor is settling time. Okay. Because we are interested in knowing that how the system changes from the transient behavior or system performance changes from transient behavior to the steady state behavior. And so, what happens that these oscillations will keep on going for a very large amount of time. Okay. So, to get the settling time, what is usually done is that we allow certain percentage of the steady state value as the variation, and we find out that amount of time after which that particular value has reached. Okay. So, for example, here in this figure, as you can see that we have allowed this variation to be 2% of excess. Okay. It is the 2% of excess, and that is taken as the that variation has been taken for finding out the settling time. So, it measures the time taken for the oscillations to die away. Okay. And it is measured by time taken by response to fall and remain within some specified percentage of the steady state value. Okay. So, to fall and remain within that specified percentage of the steady state value, we can talk about say 2% value, or we can talk about 5% value. Okay. So, if we are considering say the 2% value, so it means that the amplitude of the oscillation should be less than 2% of the excess. Okay. So, that is what is called this time Ts corresponding to that where the amplitude of the oscillations remains within 2% of the axis, that is what is called as the settling time. So, we can find out what will be the expression for the settling time. Again we go for the behavior of a second order under damped system, and we have seen the behavior given by this expression, okay, where xs u is the steady state value and other parameters we have already defined. Now, here again as we have seen previously, if I put at t is equal to 0, the x is equal to 0, that we know. So, if I put it here, I get the value of p is equal to minus xs. Okay. So, I can put this value of p. So, my this x minus xs or the overshoot value is this one. Okay. Now, the maximum value will occur when omega t is multiple of pi, this we have already seen. Okay. And when the omega t is multiple of pi, then we know that the sin omega t terms will be 0 and cos omega term will be 1 always. Okay. So, in this condition, suppose we are talking about say 2% of the settling time, then the time when magnitude is 2% of excess, that we can find out. Okay. So, let us in this case, what as I said, we are talking about x minus xs as 0.02 of the excess value. Okay. X minus xs is 0.02 of excess value. So, I can just say that 0.02 into xs is equal to this expression xs e to the minus eta omega n ts. Okay. So, this I can substitute it here, and then and this expression I basically got it from this term. Okay, because I am making this as 1, I am making this as 0, and I am interested in absolute value. So, this is what I am getting it here. Okay, and when I take the log of both the sides, this is what I get, or I can round it off, and this Ts I get as 4 by eta omega n. Okay. So, this is my settling time corresponding to 2% of the value. Okay. That is the 2% of the amplitude of the oscillations. Okay. That is the steady state value. Fine. Now, if the settling time corresponds to 5% of the variation in the steady state value, then we can see that this expression turns out to be, here numerator we are going to have the 3 and rest of the things remains the same. Okay. And it is this Ts value which we are interested in. Okay. And this basically tells us that how quickly your system transforms from, or his behavior transforms from the transient behavior to the steady state behavior. Then we may also be interested in knowing the number of oscillations. Okay. So, if we want to find out the number of oscillations, we can get it by dividing the settling time by the periodic time. Okay. So, if the settling time Ts corresponds to say 2 percentage of the steady state value, the number of oscillations will be this settling time divided by the periodic time, which is 2 pi by omega. Okay. Or I can just simplify this expression, this omega goes up in the numerator. So, this is what I get, and this omega is nothing but omega d. So, I can substitute for this omega as omega n under root 1 minus zeta square. So, this is what I get, and if I simplify, I can find out the number of oscillations, and you can see that this expression is in terms of the damping ratio. Okay. So, this way I can find out the number of oscillations which are going to be there, okay, before the system gets settled. All right. Now, let us take an example to illustrate how can we find out these performance parameter. Okay. So, say the system equation for step input is given as this one. Okay. So, this is a second order system, as we can see, d square x by dt square plus 5 dx by dt plus 16 x is equal to 10 y, and say I am interested in finding out for this expression the underdamped angular frequency, the damping factor, say the damped angular frequency, rise time, peak time, say maximum percentage maximum overshoot, and say the 2% of the settling time. Okay. So, I can find out that. So, we know for a second order differential equation of this form, in the last sub module we have seen that if my general differential equation second order differential is of this form, say a2 d square x by dt square plus a1 dx by dt plus a0 x is equal to b0 y, for this system the natural frequency, angular natural frequency and the damping ratio can be defined as this one. These are in terms of the coefficients of the differential equation. Okay. So, for this problem which is under our consideration, I can compare this equation with the general expression, and I can we can see that a2 is equal to 1 here, a1 is equal to 5 and the a0 is 16. Okay. So, from here I can evaluate this omega n square term 16 by n, or omega n is 4 radian per second. Okay. Similarly, I can find out the damping ratio from here by substituting the values of a1, a2 and a0 here. So, this is 0.39 or the damping ratio will be 0.625. So, once I have got the natural frequency and I have got the damping ratio, I can find out the damped angular frequency. Okay. So, the damped angular frequency I can find out omega n is equal to omega d is equal to omega n under root 1 minus zeta square. So, by substituting here I get this omega d as 3.122 say radian per second. Now, we know that for the rise time omega tr is equal to pi by 2. So, from here I can get tr value pi by 2 omega, and this omega is nothing but the damped natural frequency here. okay, angular frequency. So, I just put pi by 2 omega d, or I substitute it here and I get the rise time as 0.5 second. Okay. Similarly, I can get the peak time by putting omega Tp is equal to pi, and if I substitute value of omega here, which is nothing but omega d, I get the peak time. Okay. And I can find out the maximum percentage overshoot, because I have already determined eta value. Okay. So, I can find out the maximum percentage overshoot here by substituting the value of eta here, that is the damping ratio, and I get this value as say 8%. Fine. Then I can find out the 2% settling time, and that is we have seen 4 by eta omega n, and this is say 1.6 second. Okay. So, with this I would like to end this lecture. These are the references which you can go through. The Bolton book by Bolton on mechatronics, Pearson and Ogata modern control engineering from PHI. Thank you.